Hi there. What we're going to look at is basically what I'm just going to call a potato launcher, launching this potato pea up in the air at 500 feet per second, which is actually a bit too fast for a potato launcher. But anyway, regardless, I think it would be beneficial for us to realize the effects of gravity and how just a one-shot velocity, and see how long it takes to diminish until you hit that point, that peak where it just stops in midair for a second and then starts to go down. So what we're looking for, and I'm just going to draw us a little scaled model here, is if we were to launch something upwards, we want to know the time it would take for it to stop before it starts to come down again. So t equals what at that point? And that's not uncommon, because you'll find a lot of even curvilinear problems. You'll need to find points such as this. So you have to kind of think, take a step back, and think about it logically. And what do we know about this particular point right here? Well, we know that the velocity is equal to 0 at this exact point. That's when it stops. It's no longer moving if you were to shoot it straight up. So what we could use is we could use this equation, V2 is equal to V1 plus AT. We could use this function, since we know A, we know V1, and we're trying to find t, so, and we even know what v2 would be, so the only thing we wouldn't know is time. First off, v2 is going to equal 0 feet per second, and that's the velocity at the point of the peak. v1 is going to equal 500 feet per second, and that's the I don't know, the muzzle velocity or whatever you want to call it. The acceleration is going to be negative 32.2 feet per second squared, and that's gravity. And then you have t, which we don't know. So if you solve for that, what you're going to have is 0 equals 500 minus 32.2 t, and that equals 500 equals 32.2 times t, and when you solve for t, that equals 15.33 seconds. Now that is the quickest way to solve for it. There are other ways, and I am going to show you. One way that one could look at this is by saying, well, A is equal to dv dt, which, mind you, that this is where that is come from. So, I mean, essentially you're doing the same thing, but I just wanted to show you that you really can pull it from the foundation. And that just means Vn, or V2 minus V1 all over T2 minus T1. Well, just realize that you have an A, which is going to equal negative 32.2. So that's negative 32.2. Then you have Vn, or V2, which is going to equal 0, V1, which is going to equal 500. You have T2, which we don't know, and we have T1, which we know is 0. When we plug this in, we get negative 32.2 equals 0 minus 500 all over T minus 0, which equals negative 32.2 equals negative 500 all over t. And when you solve for t in that instance, t is equal to negative 500 all over negative 32.2, which equals 15.33 seconds. Kind of nifty, same thing. The one on the right is from more of a foundational basis, so I just wanted you to realize that you can trust the clouded equation here. Just realize what the assumptions are. What was the difference? Notice that we had to make the assumption right here that T1 is equal to 0. That was a big assumption that we made when we looked at it from the foundational view. But as long as you know, or you just consider that your initial point is t equals 0, then you can just run with the clouded equation and not have a worry in the world. Anyway, let's continue on with another example.